Well, nice to meet you, everyone, and thank you so much for coming. And I also wanted to thank the WILDLABS team for putting this together and inviting me along. So what we're going to be doing today is talking through the basics of machine learning. So kind of what is machine learning? Why is it an interesting tool? And then I have my own unique spin on this, which is machine learning on tiny devices, which we call TinyML. So that's going to be my kind of angle I come at this with. So I noticed in the chat, some of you have got a fair amount of experience in ML already. So there might be some stuff here that's very high level and basic, but hopefully with the TinyML stuff, it still gives you an angle that you might not have thought about before. And I'll be here to answer questions at the end. So hopefully this is useful for everybody, and I'm looking forward to chatting with you. So my name's Daniel Situnayake. I work as a founding TinyML engineer at a company called Edge Impulse, and we'll be talking a little bit more about that later. We build ML tooling for TinyML. I used to work at Google on the TensorFlow team, and TensorFlow is another set of tools that Google create that power a lot of machine learning that people do. I'm the co-author of this book on TinyML, which I wrote with Pete Warden, who's one of the pioneers in the field. I'm really lucky to get to do that. And previously in my career, I've done some kind of crazy stuff. So one of the things I've done is I founded a company called Tiny Farms, and we were developing technology for growing insects for sustainable protein. So that was sort of how I got my start thinking about like the intersection of technology and animals, and with a sustainability slant on there. So it's been an interesting journey. So I wanted to start out by just answering this question. What is machine learning? It's something we hear about a lot these days, but it's not always super clear. And there are a lot of different ways you can answer this question. But to me, it's just a different kind of programming, right? So there are ways to write programs. There are ways to tell computers what to do to get a useful output. And machine learning is just one of these. So if you think about traditional programming, you might have some data and you want to be able to feed that data into a program and have the program tell you something useful. And with traditional programming, the way you do that is you'd sit down and you'd analyze that data. You'd use your domain knowledge and understanding to figure out what rules apply to that data. So imagine you're building a thermostat for a house. You know that maybe you want the AC to come on when the temperature goes above 70. And so you can just write down that as a rule in a program using an if statement. And when the data comes in that says that the temperature has gone above 70, the rule switches on the thermostat. So that's how it works with traditional programming. You get your data and your rules, sort of combine those, and then out of the other end, you get a program which tells you what should be done in a given situation. So machine learning, you sort of turn that around a little bit. So instead of coming up with rules by yourself, you take the data that you have, you label it to tell the machine learning algorithm what it means, and then you feed the data along with the labels into this machine learning system, and it comes up with a program for you called a model, which is able to take data it hasn't seen before and figure out what the label should be. It figures out what the rules are based on the data and based on the labels of the data, rather than having you sit down and apply your expertise and write stuff down. So you are actually applying some expertise when you're labeling the data, but the model itself is what figures out how to generalize that to new data. So a cool example here could be a camera trap. So imagine you've got a camera trap set up on a trail somewhere, and it's got an SD card in, and it takes a picture every time there's some motion detected. So that's fine and good, but someone's eventually going to have to go and collect this thing when the SD card fills up. And if it fills up because hikers are walking past or because trees are waving in the breeze, that's not so good. You're sort of wasting time and having people do stuff that they otherwise wouldn't need to do. So wouldn't it be nice if you could have the camera know whether it is an animal that you care about or just a hiker walking down the trail? So this is the type of thing that would be really difficult to do based on rules-based programming. If you were to sit down and try and write some if statements that figure out whether it's a deer or a person that you spotted, it would be pretty hard. I'm not sure how you'd even really get started with that. But with machine learning, you can take a load of pictures of a deer and or different deer and a load of pictures of other trail users or other typical conditions of the trail. You label the deer as being interesting. You label all the other pictures as being uninteresting, and you feed those into the model. And the model will learn, and it will learn to take inputs it hasn't seen before and classify them as either being a deer or something that isn't a deer that we don't care about. And then you can deploy that model down onto the device. So the learning happens on a big computer somewhere. You take the model that's produced and put it onto your camera trap, and it's able to only take pictures of the things that it cares about. So that's something we've seen a lot of people excited about doing with machine learning. Another cool thing is detecting poachers. So imagine you're in a situation where you have to protect some wildlife. Maybe you're wanting to listen out for things like gunshots or the sound of vehicles approaching. So you really want to monitor audio. One thing you could do is send people out there to listen, but obviously that costs a lot of money and time. So a nice thing to do would be maybe we could train a model based on a load of audio samples of gunshots, of vehicles coming through, or whatever it is you're particularly trying to listen to, and then a load of audio samples of stuff that we don't care about, normal background sounds of the savannah, or airplanes flying overhead, or all sorts of typical things that you might hear that we don't worry about. Those are our two categories, and we can train a model which can discern new audio between one of those categories and the other. And so basically, once you deploy that into the field, you have this sensor which just tells you, hey, I heard something suspicious, versus, hey, things are just going on as normal. So those are a couple of interesting use cases. But there's not really much limit to the type of data that machine learning will work with. So any kind of images, including infrared images. At Edge Impulse, we're actually working with some organizations that are using infrared images of elephants, audio, loads of different types of audio data, time series sensor data. So that could be like vibration or acceleration over time. It could be temperature over time, anything that's changing over time. Positional data, so GPS sensor data, figuring out maybe what an animal is doing by what its location is. Any combinations of the above, so you can do things like sensor fusion, where you have multiple sensors feeding into a model, and the model uses those multiple inputs to determine what's going on. And then you can do many other things that are maybe less relevant to our talk today. So parsing natural language, for example. ML's very, very adaptable sort of set of tools. So there are some key terms that I want to dig into before we get any further, that are going to help us understand what's going on. So one of those is data set. So a data set is the data that you have collected about your situation, the thing that you want to understand with machine learning. So imagine you're in our camera trap example, your data set will be your photos of hikers and random stuff that you don't care about, and your photos of the animal that you care about. And the thing with the data set is it has to be comprehensive. And for a lot of these applications, it has to be labeled. So you want your data set to encompass everything that the model might see, because the model can't understand things that it hasn't encountered before. The data set also needs to be labeled so that a person, an expert, has gone through and decided, hey, this is a picture of a deer versus this is a picture of a hiker, because the model will need that information in order to understand what's going on. So the model itself is basically like the little artifact that you get once you've fed all this data into a machine learning algorithm. So you'll get some artifact out of it that in a lot of cases, you can think of this as like a software library that you can embed into something, feed inputs in, and get some output. And the application is the thing that figures out what inputs to feed in and interprets the output. So imagine, in this case, we've got a little picture of a collar around a cat. So imagine you're working out the cat's behavior based on its motion. So the application would be the code that's running on that collar that takes the motion of the cat from a sensor, feeds it into the model, and then takes the model's output and interprets it and figures out what kind of behavior it is and what it should do as a result. So training is the process of actually feeding data into the model and having it learn about what separates the different classes and what allows it to discern between the different classes you fed in. So this is a little gift from one of my favorite movies, Extra Points if you know what it is. But you basically are able to train the model to understand the data. You can't always do it. If you feed in certain types of things that can't be discerned between, the model can't do magic. The algorithm can't do magic and figure it out. So this is always going to be a trial and error process of figuring out whether you actually can get the model to train to the point that you want. But once you've trained a model, you use it to do something called running inference. And one inference is basically taking an input, feeding it through the model and getting the output. So in this case, a trained model has had a photo fed through, and the model has picked out in the picture, in the input, where kangaroos are and provided that data, and some other program has written those bounding boxes onto the image. So inference is the process of taking a new input the model hasn't seen before, running it through the model and providing an output with some kind of prediction. So TinyML is where all of this stuff gets super interesting for me. So imagine machine learning. You probably think of big servers, big computers, like AI, like Skynet kind of crazy things like that we've all learned about from our favorite sci-fi movies in the 80s and 90s. And this was really the case until recently, that if you were doing machine learning, you were talking about running stuff on big, hefty hardware. But thanks to advances in technology over the last few years, so that's improvements in algorithms and improvements in hardware, it's now possible to run machine learning models, and we're generally talking about inference rather than training, on really small devices. So this is an example. This is a little microcontroller development board made by Arduino. It's called the Arduino Nano 33BLE Sense. And on this board is a chip, which is the processor at the heart of it. It's called the Nordic NRF 52840. And that's a tiny little computer. It has a tiny amount of RAM, 256K of RAM. It has about a megabyte of storage. So that's the whole space it has for its program, for any model you put on there. And it has a processor running at 64 megahertz, which it sounds super slow these days, but I remember when that was like way faster than my desktop PC. But the crucial thing here is this thing uses tens of microamps at a low voltage. So it's really, really power efficient. And so TinyML basically is the idea of running machine learning models in inference on these types of tiny little devices. And the things that enables you to do are amazing. So some of the things that aren't TinyML that you may have heard of are things like the Raspberry Pi. Raspberry Pi is basically like a powerful computer in a small package. It uses a lot more energy than these types of things. Same with these types of ML accelerators you might have heard of, like Google's Coral devices. They're designed to be small and compact and not as power hungry as a big server, but they still are way more power hungry than these type of TinyML devices. So there's a difference between the two categories. You can do amazing things with both, but it's interesting to think about what you can just do with TinyML. So TinyML means small, cheap, efficient hardware, low energy use, so you have amazing battery life. You can deploy these things in the field forever, literally months and months or years on a single battery. There's no need for communication because you're doing all of this ML stuff on device, so you don't need to send any data to a server, which is amazing if you're somewhere that doesn't have good connectivity. It's also amazing for saving energy because communications is usually the thing, pardon me, that costs you loads of energy. And the thing that I find really exciting about this is it gives you potentially perfect privacy. So imagine our trail cam. no one who's hiking on a trail wants to be photographed by some random researcher, even if it's for the good of science. So if our camera can avoid taking pictures of hikers, that's great. That gives people better privacy. And so that's exciting. So I'm going to talk about and show you a use case for TinyML in something that's like personal to me. So I live in Northern California, which means I cannot afford a house. So my stand-in for having a garden is this little balcony that I'm very lucky to have. And my girlfriend and I have put a bunch of plants out there, and we feed the birds, and we have a ton of nice birds and less nice squirrels coming to hang out on our balcony. And so I started thinking, like, wouldn't it be nice if I could understand which kinds of birds are visiting my balcony and how often and what times of day using machine learning. And so this is the little toy project that I'm going to show you a glimpse of today. And so it's going to help me walk through the workflow of machine learning. So the first thing we need to do is figure out what we want to do. So in this case, I want to know which birds are around based on the sounds that they make. Okay, so pretty simple. Figure out if I hear a certain bird sound, I want to tally it up. And we can then figure out what to do with that data later. So the second thing we need to do is obtain a data set. So that is generally the most difficult part of any machine learning project. Data is like a sort of valuable and precious resource. The third thing we need to do is train a model, and I'll be showing you an easy way to do that. The fourth thing is this iterative process. So you train a model. First time you train it is probably not going to work that well, and you need to tweak it. There are things you can adjust about the model, like knobs and dials that you can change to adjust how it works. And you'll need to experiment with it a little bit and maybe add more data until either it works or until you've proven that it won't work. Sometimes it's just not possible to do a good job of something. The next thing to do is deploy the model. So this is when you take the model that you've trained on a computer and deploy it down to one of your tiny devices or to where it's going to be living. And the sixth thing, which is super important, is to monitor the model over time to make sure it's still working, make sure it's still doing the thing that you expected it to do, because stuff can change over time. We'll talk about all of that later. So what we want to do is identify when a particular species of bird is singing. We want to train a tiny model that will run on embedded hardware. And we want to start with just one or two species, because this is less complex. The less the model has to do, the smaller and easier it can be. So because we want a model running on tiny hardware, we're going to start with just a couple species of birds, and we'll see where we can go from there. So obtaining a data set, like I said, that's often the most challenging part. But luckily for us, there is an amazing resource. It's called xenocanto.org. And this is basically a crowdsourced set of bird audio recordings. So you can search for species of birds, and they have a ton of recording for the common ones, and you can download them. It's really awesome. So what I have done is picked a couple of birds that visit my little balcony. So one of these, my favorite, is the oak titmouse. It's cute, gray and angry. They're really, really sweet. And then the mourning doves, which are very soothing. They eat a huge amount of food, and they're usually mating about 3 times on my balcony every evening. So these are the two standout characters of the balcony that we're going to try and detect. It's also helpful because they make very different sounds. I'll play you some examples in a minute, but that's going to be very helpful to help our model differentiate between them. So preparing data is often the most time-consuming thing in ML. So it's really important that the data is clean, well labeled, doesn't have invalid samples. You might have to pull together data from different sources to make your overall data set. And this is something we often do using scripts. So for this, I actually wrote a script which pulls down the data for birds that you care about from Xenocanto and cleans it, or it doesn't clean it up, it sort of chops it up and mixes it with some other data sources so that we have nice balanced data sets of birds along with noise, background noise, and that's very important. So this script is going to be available if anyone wants to play with it. I'll show you the link at the end. So now we've got our data set. training models is the next step. And this is a huge question. How do we train models? There are a million different ways. You can go super low level and write code yourself to do it. You can use libraries and frameworks that make it a bit easier. But I'm a little bit biased because it's the company I work for. But I think like by far the easiest way to train an ML model right now is using our tool, Edge Impulse. So this is our little marketing slide, but basically we allow you to upload or capture data. We walk you through the process of processing and training a model, and then we let you deploy it to a bunch of different devices. So you can either download your model as a C++ library that you can embed into devices, or you can have a pre-made firmware that you can flash directly onto the device. So this is what we're going to use because it's super quick and easy. So I'm going to switch over now to the Edge Impulse UI. Actually, first I'll give you a glimpse. This is the Bird audio download script. So here I've just specified a couple of bird species that I want, and the script can grab that data and then I can upload it to Edge Impulse. So once I've done that, I end up here. So this is the Edge Impulse UI. Let me make it a little bit bigger for you. So here you can see we've got a bunch of data. We've got like an hour of data, which is a nice amount. I've got a little graphic here which tells me I've got equal balanced amounts of data roughly for 3 different categories. So that's my 2 birds, and it's also noise. So remember I said that it's really important that models have have been exposed to all the things they need to be able to understand. So that means if I trained a model with just the bird audio, if the model heard anything that wasn't a bird, it wouldn't know what to do. It would randomly choose one of the birds, essentially. So I've also got this category of background noise where I've got a load of data of different types of noise that you might encounter in the world, like machine noise, like normal background household noise. And that's a 3rd category, which allows my model to sort of figure out, hey, this isn't one bird or another, it's probably this 3rd category. So we can actually use it for useful stuff. So if I play you a sample of audio, you can hear what our mourning dove sounds like. All right, there we go, very soothing. You can also see that this audio clip is 8 seconds. The first half of it is just nothing. It's like a background noise, and that's not really good for our model because we're telling it this is a mourning dove, but we're actually feeding in some audio that is just silence. So I'm going to show you something here. So what we want to do is tell our model or tell our pipeline that we're going to feed in data, and you need to chop it up in a certain way that helps make sure there's always some bird sound in it. So what I've done here is if you think about the way that the data is processed, we're going to take a window of the data and feed it into our model. So in this case, we're taking a 3.5 second window. And so hopefully that's going to be enough. If you take 3.5 seconds of data out of any sample, it will capture some of the bird song. It's long enough that it will capture some of the bird, even though the mourning doves have a little pause between their kind of sequences of calls. And then we have a window increase. So every 3.5 seconds of data, we'll take a window, and then we'll move to 2 seconds, and we'll take another window. So we get a bunch of overlapping windows. So it takes our hour of data and expands it into even more. And then the data is fed into something called an MFCC block. So this stands for mel frequency cepstral coefficients. This is a way of processing raw audio data into a form that's more suitable for passing into a deep learning model. It takes it from this crazy high frequency, difficult to understand, high bandwidth data and boils it down into something that looks more like an image. So you can see here on the right, this is an example of the image that gets fed into the model that represents the audio. And you can see in this clip here, we've got some background here. It just results in this kind of scattered pattern. And if I move this over so it captures some of the bird audio, some of the mourning dove sounds, you can see how it makes this very distinctive trail on our image. And this is what our machine learning model is going to learn to see. So it's not just taking in raw audio, it's taking some processed audio. The other cool thing you can do here, so you can just accept all these default parameters. There's a lot you can tweak if you want to play with it, but we try to pick sensible defaults so you don't have to. Once you have done that, you can look at a visualization here using an algorithm called UMAT, which basically figures out how to separate and plot these audio samples on a graph to show whether they can be distinguished from one another. And what we can see here is broadly on one side, all of our titmouse samples are showing up here. And on the other side, it's mostly mourning dove. And in the middle, it's mostly noise. And there are a bunch that are scattered throughout. And I would dare say those are things like those segments of silence that we saw earlier that are polluting our data set. So we could probably clean up our data set a little better, but at least we can see there is a general trend of things being in one place rather than another. So that's a good sign. That helps us know that this is a problem we can maybe solve with machine learning. So what I'm going to do now is actually train a neural network. So we've got a network here. Once again, you open this in Edge Impulse, we select a network that seems like it will probably work with your type of data. So you can, we love this idea of sensible defaults. So then you can get started really quickly just by clicking Start Training. So this model is going to be trained on the data that has been fed through that MFCC block. And you can see here training is happening. You can see the loss and accuracy values. Those are indications of how well the model is fitting the data. And you can see our validation accuracy, which indicates how well the model is performing, is broadly going up here. So that's a good sign. So right now it's about 76%. Going to let this run a little bit longer, and we'll be able to see how good a model we can train. So this generally doesn't take that long because we're training tiny little models and relatively small data sets. So we're now optimizing the model so that it will run well on a little embedded device. And we can now print out some performance metrics. So we can see our model's getting about 80% accuracy, which is awesome. Predictions are being outlined here in a confusion matrix, which shows, hey, this is what the expected label is, and this is what the actual label is. So you can see it's working pretty well for noise and titmouse. Most of the noise samples are being correctly predicted, and most of the titmouse are as well. But with the mourning dove, because it has those big breaks in it, and because of the way it calls, a lot of these labels are being misclassified. So we know our model works a bit better for the titmouse and the noise than it does for the mourning dove. But we can also tell our model is only 5.8 kilobytes, and it uses about 28K of RAM. So it's easily going to fit in that device that we looked at earlier. So I can show you another thing, which is if we go here, we can actually deploy the model to a particular device. So let's just pick this Arduino board. And we have a tool as part of this flow, which lets you see how well the model is performing on your test data set. So when you're training a machine learning model, it's really important to always split off part of your data and keep it until the very end, where you will run the model over it and see how your model works on data that it's never ever seen before. And so we've done that now. We're seeing we're getting 77% accuracy with data we've never seen before. And we can see again our confusion matrix here. We're getting good performance for the titmouse and the noise, not so good for the mourning dove. So that gives us a hint of where we might need to improve this model, but it's good enough for now. So I'm actually gonna demo this. So if I go to the Devices tab, one of the cool things with Edge Impulse is I can load this model up on my phone. So I just open a QR code here and then load that on my phone, and we'll now connect. And so what I'm going to do is get that model running on my phone, and then I'm going to play some bird audio. So here I've got some random YouTube videos. Presumably this data is not in the Zeno Canto dataset. It may be, hopefully not. here's my little friend. So what I'm going to do is hold this up. Hopefully you can see the phone, and it's going to sample some audio. Right now I'm speaking, and you can see that that shows up as being noise because it's not one of the birds it expects. But if I play this, all right, so we can see we had one misclassification of mourning dove, and then it detected titmouse. So it's actually working, and it's pretty amazing how well this works. The thing that I do want to show you, though, is remember we've only trained on these two different types of bird. What happens if it hears a different kind of bird? So I'm going to play these budgies. Oops. Oh, no, it's going to play an ad.
This is a tomato.
So when the ad has disappeared.
Hey, Dan, do you want to...
Oh, sorry.
I was just people are asking to see your phone, so have I made it big for everyone? If you click on Dan's photo, his little video on the bottom, it'll make him big. Can you see? Can everyone see it now?
Let's see. I don't know if it's showing up very well. Apologies if it's blurry. So here we've got our budgies. And we'll see how the model classifies these. All right, yeah, so unfortunately, our model thinks that this is the titmouse call. And that is because maybe it sounds a little bit like it, but more likely, the model has never seen this type of sound before. It's never been exposed to this during training. So it has no idea how to classify it. So it's going to throw it in some random class just on where it happens to fall. So the way that you'd prevent that is if you're trying to actually deploy this in the field, you would need to collect sounds, collect a data set for all the different types of birds or typical background noise you might hear that are not the ones you care about. And you would put those in your noise class or in a fourth class, which is birds I don't care about. And in that way, the model will learn to distinguish between those and the actual valuable data.
Just a quick question there, Dan.
Yeah.
The digital codecs, etc., affect the ability to recognize sounds versus like live audio?
Sorry, could you repeat that question?
Sorry, how do the digital codecs, etc., affect the ability to recognize sounds versus like live audio, for example?
I see. Yeah, so that's something you have to think about. So if you're using different like encoding forms for your audio or lossy compression, that type of thing, that can introduce artifacts to audio. And so generally it's good to train a model on data that's collected from the same type of situation that you're going to be using in production. That's what you want to do if you want to sort of absolutely make sure. But generally we found that once you've passed the data through something like this MFCC feature reduction, you're getting such a kind of compressed form of the audio anyway that hopefully it only has the characteristics, the high level characteristics we care about. So any types of minor differences that are introduced by the choice of audio codec hopefully won't show up in this unless there are major artifacts. So yeah, hopefully that's a useful answer.
So I'm also just conscious we're over time, of course. Like we kind of might be an issue, but for everyone, we're going to keep Dan, if you're happy to stick around.
Yeah, absolutely. Sorry for rambling on too long.
No, it's wonderful. Sorry to everyone sticking around. So we'll let you finish and then we'll take a couple of questions. So
okay, awesome. Yeah, I have just a couple slides left. So I wanted to point out. So now we've walked through like what a workflow using ML looks like. Obviously, there's a lot more to it, but this is a good entry point. Gives you an idea of what the process looks like. And it ends with deploying it to a device and then testing it in the field. So the thing you need to ask yourself, though, is, am I going to use ML to solve this particular problem? It isn't always the right tool. So ML is really useful when you have loads of clean labeled data. So as you saw, we had some problems with the Morning Dove because it basically didn't have clean data. Like we had recordings of Morning Dove, but every 5 seconds the Morning Dove shuts up and you have this background noise. And so it's really confusing for the model. So really we'd need to spend some time cleaning that up. The other thing that we need to do is have a tightly scoped problem. So you're not going to be able to train a model that is able to identify a new species of bird that you've never heard of that is coming into the space. Like you're not going to be able to train a model that like is able to adapt to loads of different scenarios. Generally, you're going to want to train a model that works in your particular use case in the place where you're deploying your hardware, because there are models that can be big in general, but they're large. They use a lot of resources to run. And so if you're trying to deploy this stuff in the field, you need to keep things tightly scoped so you can keep the performance good. The smaller the model, the more difficult it is for the model to do its job. So you need to keep things easy for the model. And ML, you should only ever use ML if some margin of error is okay. You should never use ML if there's like a chance that your 10% chance of a mistake is going to kill someone or cause some horrible problem or like result in a policy decision that is bad. You need to make sure that it's okay to have some margin of error, because ML is a probabilistic set of approaches. You don't get yes or no out of an ML model. You get a probability of yes versus no. So when conditions may vary beyond the original data set, don't use ML. It won't help you. There are some approaches you can use for things like anomaly detection in certain circumstances, to recognize if, hey, things are normally like this and they stopped being like this. But broadly, you need to have data in your original data set. You should never use it when there's no tolerability of error, and you can't really use it if there's no data available. So to get started with this stuff, the software I just demoed to you is Edge Impulse. It's a really fun way to get started. And we've got an audio classification tutorial you can work through that will show you all the steps to do what we just did. The Python script that I've written to download the bird data sets, it's kind of ugly and crazy and hacked together from some other stuff that I had. So it's not the most beautiful code, but you can grab it here and run it, and you can add your own bird species and it will download them as long as there's data on Xenocanto. Our TinyML book, we actually have the first 6 chapters for free on tinymlbook.com. So definitely recommend grabbing those, and it has a good like intro to ML and walks you through the basics. And then you can follow me on Twitter. I tweet about all sorts of random stuff, mostly ML related. And Edge Impulse, we tweet a bunch of stuff to do with embedded ML and ML on the edge. So sorry I've overrun so much. Thank you for sticking around, and I'd love to answer any questions people have if we have time.
We had a lovely just stream of messages saying thank you, please keep going. So thank you for hanging around.
Thank you.
Thanks everyone for sticking around. Okay, we do have some questions, quite a few questions. Who was my first one? Tom, was that you? Do you want to jump in?
Let's have a look. Is my microphone working?
It is. Do you want to turn your video on as well so we can see you?
Yeah, sure. Let's turn my
No
camera
pressure. Sorry.
on. Oh, no, that's fine. I don't mind. My desk's a mess because I got Arduinos and stuff all over it. That's fine. I got a few questions about using Arduino NanoBle Sense.
Awesome.
The first one is, what's your experience using a microphone on it to record data? Because I've recorded some data with mine, but it doesn't really come through that clear sometimes. So I'm just wondering whether it's good enough or not.
Yeah, so I haven't done a sort of huge amount of testing and comparison, but we actually have a firmware available for the Nano 33BLE Sense in Edge Impulse that lets you capture audio, and for the stuff that I've used it for, it works pretty well. I haven't done any like dumping audio to an SD card or something though. It's only been like short clips and in my office basically. So
yeah, that's pretty much what I used Edge Impulse for as well, because I went through your tutorial and tested it. But I was just whistling into the microphone. I didn't actually get any bird sounds, so just kind of imitating birds and things like that just to test the quality of the audio. But yeah, I need to test it in the field first.
Yeah, so one thing, I mean, the characteristics of the microphone have a big impact, but also the enclosure. So you're going to get things like wind noise and like strange sounds. So it's important to have a similar environment for the sensor as the original audio was captured. Otherwise, you're going to get these other artifacts. There's like a lot of depth to like thinking about getting this to work the same in the field as it does in your home office.
Yeah, it's very quiet in my office. Another question is, you said that you could, what was the limit of birds you could recognize per device? Maybe about 2 tops.
Well, so I picked 2 because it was working pretty well, and I just like the example of the mourning dove because it doesn't work that well, and it gave me the opportunity to talk about the problem with the windowing and the noise. But there isn't really, so it depends on how big you're okay with the model being. So our model, I think it was about 6K. So that's tiny, you know.
Yeah, that's small.
So even if we've only got 1 megabyte of flash and 256K of RAM, we could have a much bigger model. And the more classes you add, the bigger you probably want to make the model so that it can kind of store enough information to discern between those different classes. And so that's one thing that determines how many classes you can have. For example, like vision models that are designed to run on something as powerful as a mobile phone might be able to recognize 1,000 different classes of image. So you can get pretty extreme with these things that are like a couple of megabytes. The other thing to think about is certain types of birds sound similar, and if it's hard for a person to discern between them, it will be hard for the model as well. So there might be some combinations of bird that don't work very well, especially if you have messy data. The real killer is when you have a recording that has 3 different birds in it.
You can't differentiate at all. You need to run like algorithms to break up the audio first and then analyze all that. And yeah, it gets really complicated. But I wouldn't expect like an Arduino Nano to be able to do something like that on the fly.
Yeah, so you can kind of think like, hey, maybe it's okay if I know it was one of these 3 birds for my study. So the model doesn't have to always be perfect. You can kind of work within the limitations of the technology if you need to.
Okay, I was thinking like if it could only do 1 or 2, it could have individual Arduino Nanos listen for different bird calls and make different kind of bird modules, so to speak.
Yeah, absolutely. And there's also an approach using hierarchical models. So you have a model that determines, is it this group of bird or that group of bird? And then you have other models which figure out exactly which one. And then the models can be smaller individually.
Yeah, kind of waterfall. Okay, interesting. All right, that's me done.
Awesome. Dan, do you want to jump in?
Sure. Can you hear me?
Yeah.
So see you. Nice.
Okay. I'm a huge fan of Edge Impulse. I really love what you all are doing. So I have a question about something you said about capturing data using the NanoBle Sense, because there's no really good libraries out there right now for like saving the data to SD card. Where I did a project where I wanted to like basically drop a thing in the desert and have it record overnight. So I ended up building something with the Teensy, which you can kind of see here.
Oh, awesome.
And the Teensy has really good out-of-the-box like audio processing libraries and like examples for recording onto an SD card. But I think I posted on the message board about it. You said that if you train using a data set from the Teensy, when you run inference on the Nano Sense, the microphone's different, so it might like sound different. So I mean, the actual sound might be different, so it might not be able to recognize the sounds as good. So I have if you want to, first of all, test how is it actually sounding on the NanoBle Sense in the field. There's no way right now, it seems like, to verify that it's like what it's actually sounding like. It seems like if you just have it out there and you want to do some in the field testing. And also, is there any plan to support running inference on the Teensy?
Yeah, so it's a good question. So for that specific hardware, you should drop me an email with some details of it, and we'll have a look. And you should be able to run inference on anything that has enough RAM, memory, and supports C++. Sorry, RAM, fast enough processor, and supports C++11. Drop me an email at dan@edgeimpulse.com with some details. But in terms of the audio question, it really is, it's so sort of situational. It's like use case specific. There might be some things for which the difference in the kind of qualitative experience of the microphone doesn't make much difference. But there might be some where they do. So for example, maybe one microphone has a really bad low frequency response and the other doesn't. If you're listening to little oak titmouse sounds, it probably doesn't matter that much. But if you're listening for the mourning dove, it would. So one thing you can do, I guess, like capturing data on the Arduino alone is difficult, but you can get third-party or like separate components that you can use to log data that give you like a digital interface for shunting data onto some kind of storage. So you might basically have to do that if it was really important to do that, get that realistic capture from that device in the field. So there's also probably stuff you can do looking at the data sheets for the microphones and looking at the responses and seeing whether they're comparable. But it is a tricky problem. Yeah, it's like data is like a scarce resource. It's always hard to get data at all in the first place, let alone data that happens to be recorded on the exact device that you want to use. So where that is the ideal, sometimes you have to make compromises, and it all depends on whether you can get away with it for your particular use case.
So I had some questions from Nick, who doesn't have a mic. I'm not sure if he's still on, but he basically says, he's got two questions. One is, I'm still a little bit skeptical about how machine learning can be used. How feasible is machine learning for smaller conservation NGOs as a tool to actually solve their own problems? And he's also heard that ML is basically just running a lot of logistical regressions. I can totally imagine it's beneficial for some of the scenarios you're mentioning, but for academic purposes, wouldn't you really want to be in control of the rules or how they're derived from the model?
Yes, so that's a really good question. And it actually is like, I mean, that's what I was trying to get at in those last couple of slides, is that ML isn't the right answer for every problem. There are big categories of things where you do need to know exactly what the model is doing and why it's making the choices it is. And in that case, I mean, ML broadly does include some types of model that are explainable. So what I've shown off today is something called deep learning, which is like neural networks, basically. But there are other types of machine learning model, things like decision trees, which are a little bit more understandable and explorable. And you can get more insight into how they're working. ML works, you know, if you can give a good representative data set to your model, it will learn to generalize to things it hasn't seen before. ML is a proven technology for being able to do things like make predictions based on inputs that are similar to inputs it has seen before. Whether it fits your particular use case is something that only you can determine. What is nice now is that previously it was so inaccessible, it was so hard to get the training and knowledge to be able to work with ML, that the doors were closed to most people unless you're going to send one of your employees to do like a year's study to get up to speed. But nowadays the tooling exists that every developer can start to build and train and evaluate models with this stuff. And so if you have the question like, could this work in my particular case, maybe you can start to get an answer to that question in a matter of days rather than like years, which is really important. So yeah, it doesn't work everywhere. It's important to evaluate, and hopefully with tools like Edge Impulse and like some of the other options that are out there, you can do that evaluation a lot more quickly and figure out if it's going to work for you without wasting a lot of time.
Rob, do you want to jump in?
Hi, Dan. Can you hear me all right?
Hey,
We
yeah,
can.
perfect.
Fantastic talk and really, really interesting. I just had a very quick question about the number of files for each of the individual species that you used in your model. You mentioned that you had about an hour of data, but what did that break down to in terms of individual files of each species?
Yeah, that's a good question. So the way I did this, and you'll see in the script that I've posted that link to, and then I can pull that up again, actually, if it's... Oh, let me do that in a minute. So basically, Xenocanto, it's this sort of crowdsourced database of bird audio. And so some of the samples are like an hour of audio. Some of the samples are like 3 seconds. And so what I had to do basically was grab all the samples I could find for a particular species and then throw away any that were too short. And then for the rest of them, I cut them all into 8-second length chunks. And the reason I did that was so that I could mix them up evenly. So I guess it's a little complicated, but because I wanted to have a test and training set, I want the training set to be 80% of my data, the test set to be 20% of my data. And so in order to get balance between the different samples and also between the different types of noise sample that I have, so that if I just did a random sampling of them, I might end up with no samples in my test set of certain types of recording from certain files. So to minimize the risk of that, I cut all the files into 8-second chunks and then try to take an equal part of each type. And that was what formed my data set. So it's a bit of a long-winded answer. But essentially the file lengths all varied horribly, and I tried to rationalize that a bit before cutting my data sets up so that I got a good balance of data in each data set. Does that help?
Yeah, I mean, it's I guess for us who are kind of, you know, someone like me, a novice, one thing that I always hear is that the more data, the better. And one of the things I guess that interested me about your approach was that collection of data that people have. If that keeps getting added to and more people upload, you know, a titmouse noise or whatever, do you think that's how you solve the problem of classifying, you know, mourning doves and titmouse better? Or are we talking thousands and thousands of individual files needed for most models?
Oh yeah, good question. So yeah, it is basically the more data you have, the better, always. And the thing that's crazy is you can never really stop, because there's this phenomenon where, imagine you train a model on audio data that's collected today. You've got you could have an infinite amount. You train you've got 1 million hours of oak titmouse recordings and mourning doves. And you can train a model that works really well. But then in 10 years' time, when a new brand of airplane becomes popular and it makes a slightly different engine sound and that starts flying over, your model's never heard that kind of background noise before. And so the data set that you have, even though it was really comprehensive at the time, it isn't going to be able to understand what's going on there. So data is it's a constant effort to keep on improving your model with new data. The world changes around us and we have to sort of keep pace with it. So it's this endless journey, really.
Thanks, Dan. That's fascinating stuff. Thank you very much.
Thank you.
Maxine, do you want to jump in?
Oh, yeah, can do. Can you hear me okay?
We can do.
Perfect. Thank you so much for this talk. It's been super useful. I'm completely new to this kind of stuff as well. But basically, I'm going to be doing a study looking at gunshots and primate calls. So we're basically using audio MOFs, Bushnell cameras, and possibly SM4s to collect our data. And I was just wondering more on the deployment terms of things. We have all the data. We definitely know that we want to teach an algorithm so that when we conduct field seasons in the future, we can just identify things in real time. I've just got a simple question about the hardware. Is Edge Impulse something that I could input all this data onto, teach my algorithm, and then put the algorithm onto those same machines? Is that something that it would be able to do?
Can I jump in as well? Another question that's come up a couple of times is, does AudioMoth and your stuff, are they integrated? Do they work together?
Yeah, I don't remember off the top of my head, and I don't want to say something that's not.
If they don't, how long until they can work together?
Yeah, let me see. So you can definitely, obviously, take audio that's recorded with the AudioMoth. Okay, so the AudioMoth itself, the microcontroller on there, it is relatively low powered. It would be able to run Edge Impulse. It doesn't have much RAM, so I'm not sure if you'd be able to run directly on device. So you can use the audio captured on it. It might be a struggle to get a large enough model to run on device. So in that case, the thing that we really, there are a few things that matter. Basically, it's like if you're doing audio classification, if you have a more powerful device, the model can run faster. And if you're trying to do real-time audio, so like streaming, and you know exactly when an event happens, you want it to be really fast. If you can take 5 seconds of audio every 10 seconds and run it through the model, and that's okay for your use case, then you can get away with a slower device. But for something like gunshots, where it's like instantaneous, you'd need something that's fairly fast so that the model can run quickly. Then obviously the storage and the RAM are important, because that determines how big your model can be.
Okay, we've hit the hour. I feel like double the length is probably like enough. Ellie's just dropped some links in. I thank you everyone who stayed around, and thank you so much, Dan. This was fascinating. We have another tutorial coming up next week. 10 hours, Rob, come on. We have another tutorial coming up next week, which is going to tackle getting started with machine learning for camera trapping specifically. And Sarah is a fantastic speaker. She's been a part of our virtual meetups. She's super popular. So come along. We've got about probably 100 tickets left. So come along. We also have
the link for that is now in the chat. I've just dropped it in if you want to register.
Awesome. You can find everything on WILDLABS.NET, the community. A lot of people are looking to connect with each other and find projects that need engineering talent. We have a lot of we have 4,000 conservationists and conservation tech people in our community, so that's a place to go to. The other thing I was going to say is, there are a lot of people who are interested in acoustics and machine learning. We have 2 more talks that are coming up after Sarah's that are specifically around machine learning and AudioMoths and scaling up surveys with AudioMoths and machine learning and automated processing. So do tune in for them. The registration will open on Mondays Mondays like a week and a half before the talk. So, oh yeah, Ellie's just dropped in a nice link. So thank you very much, Dan. Thank you, everyone else. I know a lot of people wanted to connect with each other, so email me if you need to be connected with someone in the chat, or tweet at us. Yeah. Okay.
Thank you so much, everyone. It's really, really nice to be able to do this, and a huge thanks to the WILDLABS team. And do drop by, like if you start using Edge Impulse and run into some problems, we're really active on our Edge Impulse forum. So if you have like technical questions about Edge Impulse, or something's not working, or you don't know if something's possible, just go there and post, and we'll answer really quick.